Assalamualaikum warahmatullahi wabarakatuh and a very good morning to all of our audience. Welcome to Bicara Pakar UIRL 2022 webinar. This is the first series which is brought to you live through Webex, Facebook Live of Department of Deputy Vice Chancellor Research and Innovation UTM and also University Laboratory Management Center PPMU. You can also catch up our upcoming webinars in our Facebook page so that you will not be missing out any updates. Ladies and gentlemen, I'm Malaha Muhammad, Science Officer in UIRL and the moderators for today's sessions. On behalf of PPMU, I would like to extend a very warm welcome and thank you to all of you for joining us today. We really appreciate your precious time. For your information, this webinar is conducted in a series starting from the year 2021. This series was successfully organized with thousands of audience who have joined us. We have called upon various kinds of field expertise among UTM researchers who have been appointed and collaborated with UIRL. And I am proud to announce UIRL latest achievement, which has been awarded with ISO 17025-2017 Malaysia Laboratory Accreditation Scheme SAM in 2021. For this year, 2022, we have 4 slots altogether, and the first and second slots were successfully organized last week by our speaker, Dr. Zamri, and Associate Professor, Dr. Zaitun. If you miss it, you can catch up the video in our UIRL YouTube channel. And for today's Bicara Pakar UIRL webinar, we will also bring to you another interesting topic. Before that, I would like to welcome our honorable speaker, Dr. Siti Ernieyanti Hashim, Senior Lecturer at Faculty Science, UTM Johor Bahru. How are you, Doctor?
Fine, thank you.
Thank you for joining us today. I believe the topic that you will share with us will be one of the important sources and knowledge for us to improve our research in the future. Okay, for all our audience, just take note that this webinar will be around 1 hour and 50 minutes and 30 minutes for the Q&A session. Those who have a question, you can write it in the chat box or comment in the Webex or Facebook Live, and the question will be raised to our speaker right after the session. Before that, please make sure your mic in mute mode to prevent background noise from disrupting the session. Attendance link will be shared in the chat box 30 minutes after the webinar begins for UTM-CPD, and archive points along with the purpose of e-certificate and video link as well. So please stay tuned until the end of the webinar because we also have some exciting quizzes that you can win, and the questions will be given by our speaker along the session. So before we start the session, let me introduce briefly our speaker for today first. Okay, our speaker is Dr. Siti Ernieyanti, a senior lecturer at the Department of Chemistry, Faculty of Science, University Technology Malaysia. She graduated with a first-class honors degree in industrial chemistry from UTM. After graduating, she continued her study in natural products field for her PhD on title Chemical Constituents and Bioactivity Studies of Selected Hornstet species. She experts in separation, purification, and handling bioassays such as antioxidant, antimicrobial, anti-diabetic, and anti-inflammatory activities. She also has comprehensive knowledge in characterization using 1D and 2D nuclear magnetic resonance, infrared spectroscopy, and ultraviolet spectroscopy. She completed her PhD at the end of 2015 and was conferred a doctorate degree in 2016. Dr. Siti Ernieyanti teaches several courses in the department and gives services to other faculties at UTM, including organic chemistry, biomolecules, and organic chemistry for engineering. She is also one of the professional members in Persatuan Sains Analis Malaysia, Analis, and Malaysian Natural Product Society, MNPS. So without further ado, I hand over this webinar to Dr. Siti Ernieyanti with the topic Step-by-Step Guide to 1D NMR Interpretation of Organic Compound. The floor is yours, Doctor.
Thank you, Puan Malaha, our lovely moderator for today webinar. Okay, good morning everyone. Assalamualaikum warahmatullahi wabarakatuh. I am Dr. Siti Ernieyanti binti Hashim, Senior Lecturer from Department of Chemistry, Faculty of Science UTM, Skudai Johor. Okay, so for this morning, I would like to share about a step-by-step guide how to interpret NMR or analyze the NMR spectrum. Okay, so for today we'll focus on the proton and carbon 13 because we focus on the organic compounds. Okay, sorry. Okay, so before we go further on the analysis of NMR, we should know first the NMR. What is NMR? Some of you maybe this is the first time you hear about NMR. So NMR is nuclear magnetic resonance. Okay, it's actually an instrument that deal with nuclei. Okay, with magnetic field. Okay, it measures the interaction of the spinning nuclei. Okay, a spinning nuclei that resonate at certain frequency. So this instrument helps to determine number of each of distinct type of hydrogen nuclei, including the wide variety of nuclei with odd atomic number. Okay, odd atomic number meaning that if you run for a carbon spectrum, carbon analysis, the inactive NMR, the active NMR will be the carbon-13 isotopes. Okay, so this is for the NMR active will be the odd atomic number nuclei only. Okay. Okay, in NMR analysis, we have two analysis, okay, 1D and 2D NMR analysis, okay. In 1D NMR, we have proton carbon NMR, okay. 1D NMR analysis is a series of signals, okay, which plotted on x-axis, okay, against the frequency. Okay, the difference is one is plotted in x-axis, while for 2D NMR analysis, the signals is plotted in both x and y axis. Okay, so in 2D, the intensity is we observe as a contours. Okay. Okay, when we go into the NMR analysis, there are several things that we need to look at. Okay, when you do analysis of NMR, there are several things that you need to look at. These are the 4 things that you need to look. Okay, so the first one is the number of signals. Okay, so the number of signals actually determine numbers of different types of atoms, protons or carbons that present in the compound. Okay, the second one is the location of the signals. Okay, it determines the shielding of the atoms. Okay, either it's a protons or carbon nuclei, so we can know the shielding of the atoms based on the location of the signals. Okay, and then the next one is the intensity of the signals, where determine if you run the proton NMR spectrum analysis or proton NMR experiment. Okay, the intensity indicate the number of protons. Okay, the last one is the splitting of signal, which is the splitting pattern for each of the signals that determine the number of protons on the adjacent atoms. Okay. Okay, so for a refreshing, we start with first quiz. Okay, because we just started, so this is like a warm-up quiz. Okay, so the first quiz, the question will be, okay, you can type the answer in the chat box. Okay, so the first quiz will be, what is the difference between 1D and 2D NMR analysis? I think the second slide will be the answer. Okay, everyone, you can type the question, the answer in the chat box. Okay, the committee and me will 1D. Okay, the dimension, the difference. What is it? Okay, Zulhanafi. Okay, sikit lagi. Zulhanafi. So 1D is plotted in x-axis only, while the 2D? So interesting prize waiting for all of you. Okay, so Zulhanafi, 2D plotted in contour forms. Okay, I think Zulhanafi is quite near because it's already stated about 1D plotted in x-axis, while the 2D NMR plotted in contour form, which is in both x and y axis. I think the Zulhanafi will be our winner for the first quiz. Okay, congratulations to Zulhanafi. For the others, don't worry. There are several quizzes waiting for all of you. So stay tuned, okay? Okay, pemalahan Zulhanafi. Okay, Zulhanafi, the committee will contact Zulhanafi, okay? Okay, so for the others, don't get upset. Okay, there are several quizzes waiting for you. Okay, stay tuned. Okay, so we go for the next things, okay? So this is the typical spectrum. Okay, when you run proton experiment, okay, there are several. This is the typical spectrum that you will get. Okay, so there are several things that you need to look at when you have this spectrum. There are several things. Okay, the first one is the chemical shift. Okay, the value on the top of the spectrum is the chemical shift value. Okay, and then on the bottom of the spectrum will be the integration, and then the last one is the splitting pattern. Each of the signal will have their own splitting pattern. Okay, so we will go one by one, what is chemical shift value, what is the splitting pattern, and what is the integration. Okay. Okay, so what is chemical shift? Okay, chemical shift is actually the value, the frequency of the spinning nuclei. Okay, we know that the nuclei is spin. Okay, so it will resonate at certain frequency. This is the chemical shift value. So the unit is part per million, ppm. Okay, we know that frequency usually is in hertz. Why does chemical shift unit in part per million in ppm? Because chemical shift actually, the ratio of chemical shift from the standard that we use is the tetrametasilene universally used, which is the TMS, in hertz to the total spectrometer frequency. So the total spectrometer frequency, meaning that if you use 400 megahertz instrument, NMR instrument, you need to divide by 400 megahertz. So that's why the chemical shift value actually is independent on the field strength. Okay, so no wonder you run with 400 megahertz or 500 megahertz, different strength of magnetic field, you will get the same chemical shift value. Okay, meaning that if you run, for example, you run one compound in 400 megahertz, okay, NMR, and then you repeat, then maybe the next week you want to have a high resolution spectrum, you run with 500 megahertz. The value of the chemical shift will be the same. Okay. And then magnetic shielding. Okay. Each of the proton in the compound actually resonate at different frequency. Okay, just imagine if each of these proton, okay, resonate at the same frequency. So not much information that you can get from the NMR analysis, right? So actually what happened, okay, each of the proton will resonate at different frequency. Why? Okay, why does each of the proton resonate at different frequency? Okay, because back to the theory, we know that a nucleus actually surrounded by an electron, by electrons, okay, the valence electron. So this electron, they actually shield the nuclei from the external magnetic field. Okay, it shield. That's why we call it as a magnetic shielding. Okay, so each of the nuclei will have different magnetic shielding. Okay, so this magnetic shielding affect by several factors. Okay, so the first one is the hybridization effect. Okay, either your proton or your atomic nuclei is sp hybridization or sp3 or sp hybridization. So each of it will have will resonate at different chemical shift value, will have the different chemical shift value. Okay, the next term, okay, okay, so to an electronegative element. Okay, so what does this electronegative atom do? It will withdraw electron from the nuclei. So the electron that shield the nuclei already been taken by the electronegative atom. So the nuclei will be less shielded. So it will resonate at high frequency, or the chemical shift value will be increase. Okay. The next one is anisotropy effect. Okay. So this effect actually the pi electron effect. Okay. The circulation of pi electron. Okay. Especially in aromatic ring. We know that in aromatic ring there are 6 pi electron. So this pi electron actually circulate. Okay, circulate. When you give the external magnetic field, that this pi electron will circulate. Then this pi electron, the circulation of pi electron will create another magnetic field. So this created magnetic field actually deshield or deshield the nuclei. So it will absorb, or the chemical shift value will be higher. Okay, the last one is hydrogen bonding effect in the proton of hydroxyl group or amino group. Okay. Okay, because of these 4 factors, okay, then we will get a chemical shift range for proton or carbon because of these 4 factors. Okay, all the proton will resonate at a range, in a range, okay? So this chemical shift range divided into two regions, okay? The outfield region or the outfield region, which or the high field region. In this region, actually the proton that less affected by all the factors, okay? Less affected, okay? Meaning that it's more shielded, okay? The more shielded proton will be resonate at the upfield region, okay? While the downfield region is for the proton or atomic nuclei that is highly affected by the factors, the hybridization, the electronegativity, okay? The anisotropy effect and also the hydrogen bonding effect, okay? Okay, so this is the value, okay, the typical value for the chemical shift value for the proton, okay. So if we can see from here, okay, the value of sp3 proton, okay, sp3 proton, alkenes, okay, the CH3, CH2, CH hydrocarbons, okay, the value, the chemical shift value is less than the sp2 proton. Okay, this one is the sp2 proton. So the proton, this is due to the hybridization. When you increase the s orbital character, okay, it will tend to deshield the proton nuclei. That's why the chemical shift value is higher compared to sp3 proton. Okay, and then the next one is anisotropy effect. Okay, the anisotropy effect, okay, sorry. Okay, the anisotropy effect, if you see from the aromatic proton, is more higher because of the anisotropy effect. Okay, it's much more higher than the sp2 proton. Okay, the next one is the effect of electronegativity. Okay, so if you increase the electronegativity of the element, okay, for example, we have the fluorine atom, the fluorine compound. Okay, if you compare with the chlorine compound, okay, the electronegativity of fluorine is much more higher than chlorine atom. So that's why the chemical shift value for the fluorine compound is higher, the chemical shift value is higher compared to the chlorine compound, the chloroform, okay? The value of chloroform is less, the chemical shift value is less than the fluorine compound because of the electronegativity. You increase the electronegativity of the element will increase the chemical shift value. Why? Because the proton nuclei will be less shielded, okay? Deshielded, okay? And then the effect of numbers of substituents, meaning that you increase, okay, the number of substituent. Okay, for example, we compare between chloroform CHCl3. Okay, in here you have 3 chlorine atom. You compare with dichloromethane, there is only 2 chlorine atom. The chemical shift value for chloroform is much more higher because there is more chlorine atom in chloroform. Okay, so we increase the electronegativity, so it will increase the chemical shift value. Okay. Okay, the next quiz. Get ready, everyone. So before that, I think we stop a while for a photo session. Can everyone turn on your camera?
Yes. Yes, please, the audience, open up your camera first. Right. Okay, Bro Setia.
Okay.
Okay.
Okay, thank you everyone.
Okay.
Okay, we're done with our photo session. Thank you everyone for your kindness to open your camera. Okay, then we go for our second quiz. Okay, so get ready everyone. Okay, so the second quiz, the question is a simple, a really simple question. What are the factors affecting magnetic shielding? So you list out all the factors, then you will get the interesting prize like Pamala has said before. A interesting prize waiting for all of you. So, DRC, so cepat sangat hybridization, electronegativity, anisotropy effect and hydrogen bonding. Okay, so we have the winner, Dian Rusti. Okay, the committee will contact you. Dian Rusti, congratulations Dian Rusti. Nura Aina, only one tak cukup. Kena list out all the factors. Okay. Congratulations to Dian Rusti. Okay. Okay, so we move to the next slide. Okay, so integration. Okay, what is integration? Integration actually the intensity of the signals. Okay, this intensity of signals is actually proportional to the number of proton. Okay, the area under the peak is proportional to the number of proton. Okay, meaning that each of the integration give you the information how many protons okay present in the compound or bonded to the carbon. Okay, so for example, this is some example. This compound, okay, the integration is 1/3. Okay, so the one actually, this one integration is actually for the 3 proton in this metal group. Okay, the 3 proton here. Okay, so once you multiply by 3, all the integration you need to multiply by the same number. So this one, the 3 integration here, you need to multiply by 3. Okay, so it's equal to 9, the 9 proton in these 3 magnetically equivalent methyl group. Okay, so this for the 9 proton, this one is for the methyl 3 proton. Okay, so we see the next example. Okay, so this one, okay, the integration will be 0.5, 1, 1.5 and 3. Okay, actually this integration you need to multiply by 3 because this 0.5 is actually for the hydroxyl proton. So you need to multiply all the integration by 2. Okay, multiply with 2. Then you will get the 3 integration here is for the 6 proton for carbon A. Okay, the 6 proton A. So this one is 6 proton for the carbon A. Meanwhile, for the 1.5 here, when you times by 2 is equal to 3 for the methyl proton B. Okay, so you need to make sure you are multiplying with the same numbers. Okay. Okay, and then the splitting pattern. Okay, the splitting pattern. Okay, what is splitting pattern? Okay, the splitting of each of the signal. Okay, the splitting pattern actually the interaction. Okay, you know that in a compound, each of the atomic nuclei will spin because the external magnetic field strength or the external magnetic field. So the nuclei will spin. Okay, this spinning actually the atomic nuclei with the adjacent proton nuclei will have interaction. The interaction between the proton nuclei with the adjacent non-equivalent proton. Okay, so this interaction we call as magnetic coupling. Okay, so this magnetic coupling, okay, the non-equivalent proton will split the signal of the proton nuclei. Okay, so that's why we can know how many proton on the adjacent atom or carbon based on the splitting pattern of the signals. Okay, so this splitting pattern follow the n plus 1 rule. Okay, so n plus 1 rule is the splitting, okay, splitting of the signal by the non-equivalent proton. Okay, so for example, okay, if the next, okay, the adjacent carbon have one non-equivalent proton, so it will split into 1 plus 1 equal to 2. So it will split into a doublet signal, a multiplicity of doublet. Okay, so if you have two adjacent non-equivalent protons, so it will split into 3. 2 plus 1, 3. So the multiplicity will become triplet, okay? A triplet, okay? So the area ratio for each of the multiplicity follow the Pascal triangle, okay? If for triplet, the area ratio is 1 to 1, okay? The intensity will be different, okay? Okay, why actually it split into 2, it split into 3, it split into 4, a quartet signal? Why does this happen? Okay, we know that these two proton nuclei interact, okay? Interaction of what? By the spin state, okay? So the spin state or the spin direction of the adjacent proton, non-equivalent proton, okay, is either aligned or opposed. Okay, they have two direction, two spin state. Is either it's aligned or opposed the external magnetic field. Okay, so if it align, okay, it align with the external magnetic field, it will resonate at higher frequency or at higher chemical shear value. Okay, so it will be here, okay, in this region. If the spin state oppose, okay, the external magnetic field strength, it will resonate at lower frequency or lower chemical shear value. That's why it's split into two. Okay, we see for if it split into triplet or three signal, okay, triplet, okay, multiplicity. Okay, you have, okay, for proton A, okay, it couple or magnetic coupling with two proton B, okay. So these two proton, okay, the possible spin state rearrangement, the arrangement of the spin state of these two proton, because proton A couple with both of the equivalent, the non-equivalent proton B, okay. So these two proton B, okay, the spin state, okay, is either both of it align with the external magnetic field, okay, so it will resonate at the highest frequency, these signals, or both of it oppose the external magnetic field, okay, so it will be the lowest frequency, and then either one of it align, one of it oppose. That's why when you have two proton, it will split into three signal because of the possible spin state rearrangement. Okay, so the same will be for quartet, quintet, and etc. Okay, so there is no problem. Okay, so we know that all the spin nuclei, the spinning nuclei interact by magnetic coupling. Okay, so how we want to measure? Okay, there must certain value to measure how strong does these two proton nuclei coupled interact with each other. Okay, so this we measure by using the coupling constant. Okay, the value that that show the interaction, how strong does these two spin state interact with each other. Okay, so the coupling constant is the difference between the splitting pattern, meaning that if you have a doublet, the distance between the first signal with the second signal is a coupling constant. So the unit will be in hertz, okay? And then it is same with chemical shear value, it's independent on the strength of external field, external magnetic field. So meaning that if you run the same compound with different external magnetic field, 400, 500, you will get the same chemical shear value and also the same coupling constant value. Okay, so and also coupling constant also give you an idea of the geometrical isomer also. Okay, for example, if the proton is a cis geometrical isomer, the coupling constant will be around 10 to 11 hertz. Okay, cis coupling. If it trans geometrical isomers, it will have a coupling constant around 15 to 17 hertz. So we can confirm the geometrical isomer for the proton. Okay, and then you can also observe ortho and also meta coupling of proton in aromatic compound. Okay, So coupling constant also helpful to know the position of proton in aromatic compound, either it's an auto position or meta position. Okay. Okay. So there is no problem if you have a proton that couple with two non-equivalent proton with the same coupling constant. So it will split into triplet. Okay, just imagine if you have a proton that couple with two non-equivalent proton but different coupling constant. Okay, so for example, okay, proton E, it couple with two non-equivalent proton. Okay, proton C and proton B. When it couple with proton C, the coupling constant is cis coupling. It's cis coupling with proton C with coupling constant of 11 Hertz. Okay. And then proton A also couple with proton B, trans coupling. The coupling constant value is 17 Hertz. So the coupling constant value is different. So what will happen? It will form a complex splitting pattern. Okay. So this splitting pattern, a complex split pattern, helps by drawing a splitting tree. Okay. Okay. Splitting tree. Okay. How you want to draw the splitting tree? Okay. For example, for proton E, okay, it couple trans coupling. We will draw the biggest, the largest coupling constant first. Okay. So we start with the 17 Hertz, the trans coupling. It trans coupling with proton B, right? So it's 17 Hertz. You draw first the trans coupling, which is the largest coupling constant, which is the trans coupling. Okay. And then each of the signals, okay, we know that it will split into a doublet. Okay. Each of these signals, okay, split another doublet because it's also cis coupling with proton C. Okay, so each of these signal will split into another doublet. That's why the splitting pattern become doublet of doublet. Okay, so it's not the same with two set of doublet. If you have a two set of doublet, meaning that one set of doublet for another proton, one set of doublet for the another proton, different proton. But this one, the doublet of doublet splitting pattern is for the same proton but coupled with two non-equivalent proton with different coupling constant. Okay, so we see another for proton B. Okay, proton B is trans coupling with proton A and also it germinal coupling with proton C. Okay, so we draw first the 17 Hertz and each of the signal we split another doublet signal. So with the coupling constant of 1.4. So it also we show a splitting of doublet of doublet. But see, if you see the distance, okay, the distance is different. Why? Because of the coupling constant for each of the proton, proton A and proton B is different. One for proton A, the coupling constant is 17 and 11 Hertz. For proton B, the coupling constant is 17 and 1.4 Hertz. So it's different. Okay. Even though the splitting pattern is the same, doublet of doublet. Okay. Okay, so we see one example. Okay, for a splitting pattern of methylene proton and also a methyl group. Okay. The integration for the methylene is 2, okay, because you have 2 proton bonded to the carbon, okay, but it coupled with 3 proton, 3 non-equivalent proton. So that's why you will see the splitting pattern is quartet, okay. This one because it's all the 3 proton is a magnetically and chemically equivalent. That's why it will form a quartet signal, okay. For a metal here, the 3 proton here, the integration is 3. So it will split into a triplet because it coupled with 2 non-equivalent proton with the same coupling constant. That's why it will split into a triplet signal. Okay. If you have a question to ask, you can turn on your mic, okay? Okay, proton NMR also, you can indicate or you can find the presence of OH and NH signals. But these signals, the chemical shift signals for the chemical shift value for OH and NH signals is based on the concentration. It depends on the concentration, okay? That's why it will have a wide range of chemical shift value, a chemical shift range, okay? If you see the orange line here compared to the blue line, okay, the orange line for the NH and OH is wider. Why? Because of the dependence on the concentration. If you have a dilute solution, okay, it will absorb at lower chemical shift value. It will have a lower chemical shift value. If you have a concentrated solution, which have high hydrogen bonding, okay, so it will resonate at higher frequency or the chemical shift value will be higher. That's why the shift range, okay, the shift range is wider compared to the other proton, okay. And then sometimes we will observe a signal which is a broad signal for OH and NH signal because of the proton exchange phenomena. Okay, sometimes some of it will appear as a singlet signal, singlet and sharp signal. Okay, so how you want to indicate, especially for a singlet signals, how you want to indicate that this signal is for OH or NH signals. So you need to test with D2O, okay? Disappearance or the absence of the signals after you add D2O, you run and the signals disappear. That indicate that that particular signal is for the presence of OH and NH signals, okay? These are the example of a broad signal of NH, okay? NH, a proton in amino group. Okay, for if you find this broad signal, there is no problem. You does not need to test with D2O. But if you have a singlet signal, then you need to test because sometimes the singlet signal might be a proton that does not couple with any of the adjacent proton. Okay, so you need to test with D2O. Okay. Okay, another quiz. Okay, this one will be the overall spectrum. Okay, with the splitting pattern for proton for this compound, the aromatic styrene. Okay, so this area actually for the aromatic proton. Okay, so we already go through proton A and proton B. So can you predict the coupling constant for proton C? You predict the coupling constant, just the coupling constant, because we know that Dr. Muhammad Nurul Azmi, okay, the splitting pattern will be doublet of doublet, okay, this one, a doublet of doublet. So you must have two coupling constant, because you have two doublet, right? So you must have two coupling constant. Okay, hint, proton C is cis coupling with proton A, while the proton C also germinal coupling with proton B. Okay, Dr. Muhammad Nurul Azmi, ada lagi yang sebelum tu ke? Doublet of doublet, Ismail. Doublet of doublet, 17 and 2 hertz. Okay, sorry Dr. Muhammad Nurul Azmi. Okay, Ismail already. Okay, because the value can be around 1 to 2 hertz. Okay. Okay, congratulations. For proton C, it's not 17 hertz because it's cis coupling. It's cis coupling with proton E. It's not 17. The 2 hertz is correct. 1.4 hertz also correct. But the 17, because 17 hertz is for the trans coupling. Proton C is cis coupling. Okay, 17 hertz is the coupling constant for trans. Okay, yin, doublet of doublet, 11 and 2 hertz. Okay, so the answer is 11 and 2 hertz. Okay, Kopoyi, congratulations. Okay, the winner is Kopoyi, Ismail. Kopoyi already answered the correct answer. Okay, so it will be 11 and 2 hertz or 1.4 hertz. Okay, so the value, the coupling constant will be around because it's predict, so you can guess around 1 to 2 hertz. Okay. You're welcome, Ko. Okay, so don't worry, we have one more questions. Okay. So finish on the proton. Okay, about the chemical shift value. the coupling constant and also the splitting pattern. Okay, so we go to the 1D NMR, the another 1D NMR analysis, which is carbon 13. Okay, NMR. Okay, so the resonant frequency for carbon 13 NMR, okay, the resonant frequency is 1/4 of the magnetic strength. Okay, for example, okay, if you use a 400 megahertz NMR instrument, the proton, the resonant frequency for proton is 400, okay, 400 megahertz. It's 100% of the resonant frequency. But if you use, but for carbon 13 NMR, it's 1/4, meaning that only 100 megahertz of the resonant frequency for carbon 13 nuclei. Why? Because of the abundance of carbon 13 isotope nuclei. Okay, the abundance is 1% only. That's why it's only, the resonant frequency is only 100 megahertz. Okay, because of this low abundance of the carbon 13 nuclei, okay, the isotope nuclei, the range of the carbon 13, the chemical shift range of carbon 13, okay, also will become wider, around 0 up to 200 ppm, 20 times larger than proton chemical shift range. Okay, so in carbon 13 also, okay, there is no integration, okay, because of the intensity of the carbon signals is unreliable. That's why the signal area or the intensity of the signal is not proportional to the number of carbon. If proton, yes, we have integration, can know that that's possible. In carbon, no, because the intensity is unreliable. Okay. Okay, so the low abundance of carbon 13 nuclei, the isotope, okay, makes, okay, you need to increase the number of individual scan. Okay, for example, if you run for proton experiment, you can use maybe 4 scan, number of scan. Okay, that's why you can finish a proton experiment within a minute. Okay, but for carbon 13 experiment, you need to increase the individual number of scan. Just imagine you want to find one atomic nuclei out of 100. So it takes time, right? So you need to increase the number of scan. So the times of throw will be increased. Sometimes up to 8 hours. Sometimes you need to increase up to 24 hours. The experiment depends on the quantity and also the quality of sample. Okay. Okay, so if we compare between the chemical shift range of proton and carbon 13, okay, experiment, okay, you will see that the arrangement, okay, the rearrangement of the functional group is the same because the factors affecting the magnetic shielding is the same for proton or carbon nuclei. Okay, the difference is just carbon 13 NMR chemical shift range, the carbon NMR chemical shift range is wider compared to the proton NMR. Okay. For example, in the Gaussian region, we have the carbonyl proton. For carbon, we have the carbonyl carbon, followed by the aromatic proton and also aromatic carbon. The same, because the factors is the same. The hybridization effect, the electronegative effect, the hydrogen bonding effect is the same. That's why the rearrangement of the functional group in the chemical shift range also the same. Okay. Okay, interpretation of carbon 13 NMR spectrum. Okay, when you want to analyze, okay, same as proton, you need to see several things. Okay, the numbers of different signals actually will indicate the number of different kind of carbons. Okay, in the compound. Okay, and then the location of signal, which is the chemical shift value, indicate type of functional group of your carbon. Okay, and also in carbon also we can, okay, observe the splitting pattern, okay, that indicate the number of protons attached to the carbons. Different with proton, the splitting pattern of a signals give you the idea of the proton, number of proton on the adjacent carbon. But in carbon, this splitting pattern gives you the idea of the proton that directly bonded or directly attached to the carbon. Okay, so the splitting pattern also follow the n+1 rule. Okay, for example, if your carbon is a methane carbon, only one proton directly bonded to carbon. Okay, so it will split into doublet multiplicity. Okay, if you have 2 proton bonded to the carbon, it will split into triplet multiplicity, 2 plus 1. Okay, however, okay, we know that the shift range for carbon, okay, wider, up to 220 ppm, 20 times larger than proton. Of course, the coupling constant also will become wider. Okay, if in proton, the coupling constant up to 18 hertz. Okay, the largest one will be the trans coupling. But in carbon-13, it will become larger because the range wider, the coupling constant also become wider. Okay, so what will happen if you have, just imagine you have each of the carbon split with a wider coupling constant. So what will happen? Of course, a complex splitting pattern which is overlap. Okay, overlap between each other will uh will happen. So it's difficult to interpret. Okay, so for example, okay, you see here we have a methyl here, the aromatic proton. Okay, the methyl here will split into a quartet. You can see the distance from each of the signal for the quartet signal is far from each other. Different with in proton, if you see the quartet, the distance is near to each other because of the low abundance of carbon-13 nuclei. Okay, the coupling constant will also become wider. Okay, so these areas still you can observe the triplet. Okay, this one also a triplet. You can calculate the coupling constant. Okay, you can calculate how many signal without have problem with overlapping signal. However, see this region for the aromatic. Okay, aromatic region. Okay, this one without splitting pattern. Okay, this one with splitting pattern. So how you want to interpret these signals? Okay, this range, this region. So this is only a small molecule. Just imagine if you have a very complex molecule or a big molecule up to maybe 20 carbon, 30 carbon. So overlapping of signal will happen. Okay, so that's why we suggest to run a proton decoupled NMR, carbon-13 NMR experiment without splitting pattern. Okay, so of course you will lose information about how many, what is the type of carbon? Is it CH? Is it CH3? Is it CH2? Is it quaternary carbon? So you will lose all of this information. You will get information on how many carbon present only. Don't worry, okay? We suggest to run proton decouple together with depth experiment. This depth experiment, okay, you information about the type of carbon. Is it CH3, CH2, CH, or quaternary carbon? Okay, so we will run, okay, three different depth experiment, depth 45, depth 90, and depth 135. Okay, each of these experiment will give you different signals. Okay, depth 45 brought all the protonated carbon signals. Okay, so the CH signal, the CH2 signals, and also the CH3 signals, except for quaternary carbon signals. Okay, so depth 90 will give you the signal for CH carbon, the methane carbon, while depth 135, it will show the signal for all protonated carbons with different fits. Okay, the outward signal here, okay, is for CH and CH3 signals. The downward signal is for CH2 signal. So different fits. So based on this depth, you can identify which one is CH2, which one CH, which one CH3 carbon. Okay, so we see one example for a citronella. A compound, a monoterpenoid compound. A citronella is a monoterpenoid compound. Usually we found in perfume, especially in mosquito repellent, okay, organic mosquito repellent, okay. If you go any drugstore, you want to find organic mosquito repellent, the main ingredient must be citronella oil, okay, one of mosquito repellent oil, okay. So this is the carbon-13 NMR, Okay. Okay, this carbon 30 NMR, okay, indicate how many carbon present in the compound. Okay, if you have 10, it will show 10 signals. But if you come from here, you are already only have 9 signals. So where is the another 1 carbon? Okay, then that's why you need to run depth experiment. Okay, okay, the depth experiment, this one is the depth 135. Okay, because depth 135 helps you to indicate which signal actually show the presence of 2 carbon in one signal. This one signal actually indicate the presence of 2 signals, 2 carbon signals, okay? Carbon 9 and carbon 5. Then you will have all the chemical shape value for all 10 carbons, okay? And then that 135 also helps to determine, okay, how many CH2, okay? CH2 in this carbon, in this compound, okay? CH2 for carbon 1, carbon 2, carbon 4, and carbon 5. Okay, this all for this CH2. And also if you realize this is there is disappearance of one signals, okay? If you see for in carbon 30 NMR, there is signals here, but in depth 135 there is no signals in this region, meaning that this signal is for the quaternary carbon 7. Okay. Okay, so finish on the proton, carbon, and depth. We will see several compounds. Okay, examples of several compounds together with their proton, carbon, and so depth spectrum. Okay. Okay, this one is for aromatic compound. Okay, disubstituted aromatic compound. Okay. So this one, if you see, is a very simple spectrum. Okay, only 3 signal. Okay, 1, 2, and 3. This one is the deuterated signals. Okay, the solvent signals. Okay, this one is the impurities. Okay, this one is one signal. The singlet signal is for the methoxyl. Okay, proton here. While the 2 doublet signal with the same coupling constant, if you calculate from here, you will get the same coupling constant for the auto coupling of proton 2 and proton 3, also proton 5 and proton 6. Okay, so proton 3 and proton 5, okay, proton 2 and proton 6 also, okay, will appear as the same signal because both of it is chemically and magnetically equivalent. Okay, that's why it will appear at the same um, signals. I think we have some question from Fikri. How do you interpret data and information using the peak evolution? For example, tumor spectroscopic evolution. Fikri, after we finish this slide, I will explain to you, okay? Okay. So for the auto coupling, okay, it should be around maybe hertz, 7 to 8 hertz, okay? So so it will appear at the same signal, same communication value, same coupling constant because it's symmetry. So it's chemically equivalent, okay, between proton 3 and proton 5, okay? And then this is the carbon NMR spectrum, okay? So from this, okay, chemical shift value, okay, you can, okay, confirm that carbon 7, the carbonyl here is actually the carbonyl acid, okay? Because the chemical shift value in the range of 164, okay, that is for the carbonyl acid, okay? So, and then the depth experiment, okay, will help to determine how many quaternary carbons, okay? In this compound, we have 1, 2, 3 carbon, quaternary carbons. So from here, there are 3 signals disappear in depth spectrum. So we confirm that this 3 signal is for these 3 quaternary carbon. Okay, carbon 7, carbon 1, and carbon 4. Okay. Okay, the next one, the next compound, okay, also a disubstituted aromatic compound. Okay, this one is different. This one is a ketone compound. Previous compound is carboxylic acid, a benzoic acid. Okay, this acetophenone. Okay, if you see the spectrum, the pattern is quite similar. It will have one singlet signals together with two doublet signals. Okay, the singlet signals here, if you see the chemical shear value is much more lower from the previous compound. Okay, the previous compound around 3.9 ppm. Okay, so for this one is around 2.5, 2.6 ppm. Okay, so this one is the same. Okay, auto coupling. That's why, okay, you will have the same coupling constant. Okay, the same similar chemical shear value. The difference is in these singlet signals. Okay, so that's why we continue to run the carbon NMR. Okay, carbon NMR here for carbon 7, okay, the chemical shear value is around 197 ppm, much more larger from the previous chemical shear value. Okay, the chemical shear value, previous one is around 164. Okay, so we confirm that this carbonyl carbon is actually for the acetyl carbonyl. Okay, the carbonyl ketone. Okay, because this region for the carbonyl ketone region. Okay, that's why the carbon chemical shear value for this acetyl carbon here, okay, carbon A, the chemical shear value is lower than the methoxyl carbon, okay, from the previous compound. Okay, and then we also run for the depth experiment, okay, to confirm how many quaternary carbon and also to determine which one is CH carbon, which one is CH3 carbon. Okay, so from the depth 135, there is no CH2 signals observed. Okay. Okay, the last one. Okay, this will be the last example. Okay, will be our last quiz for today. Okay. So this is a tri-substituted aromatic compound. Okay. So here you will observe, okay, one singlet signals, okay, and then 1, 2, 3 different signal. Previous one, you will only observe two signal for the 4 protons, okay. For this one, you will observe 3 different signals, okay, for proton 2, proton 5, and proton 6, okay. So for this one, I want you to predict the splitting pattern and together with the coupling constant for proton 6 in this carbon, okay, the carbon 6, what is the splitting pattern for proton 6? Can you predict? Doublet of doublet. Ismail, doublet of doublet. 8, which is auto and meta coupling. 8 and 2 hertz. Okay, Ismail. Dr. Muhammad Nur Azmi. Lambat sikit je, lambat sesaat. Okay, so Ismail already answer it. Doublet of doublet. 8 and 2 hertz. Okay, so it's around 1 to 2 hertz. Okay, 1 up to 2 hertz. Sometimes it can be around 2.4 hertz. Okay, so it depends on compound. Okay. Okay, so we see the carbon. Okay, so to indicate how many carbon present in the compound. Okay, so we confirm that this is a benzoic acid compound based on the chemical shear value for the carbonyl. Okay, and then the depth experiment, the depth spectrum indicate how many, there are 1, 2, 3, 4 quaternary carbon. Okay, so we can find which one is for these 4 carbon quaternary. Okay. Okay, so that's all. Before last but not least, I would like to acknowledge UIRL UTM for the opportunity to being one of the speaker for this webinar and also the Nature Product Research Group. Thank you. Okay, ada soalan kan?
Okay, thank you, Dr. Ernie, for the interesting presentation and knowledge that shared to us. Okay, I believe we do have some questions in the comment section from our audience. But before that, Doctor, can we take another session photo
Okay, sure.
before we go for the the questions. So please, the audience, open up your camera once again so that we can get another photo sessions. Okay. Okay.
1, 2, 3,
Okay.
and 1, 1, 2, 3. Last one. 1, 2, 3. Okay, done.
Okay. Thank you. And okay, doctor, we
Proceed
go
with
for the first questions that from Mr. Fikri right now, right?
okay.
Mr. Fikri.
How do you Fikri Shami, how do you interpret data and information
Yes.
using the peak evaluation? For example, tumor spectroscopy.
Spectroscopy.
Mr. Fikri, Fikri Suhaimi. Okay. Actually, the things is, okay, when you run NMR, okay, for example, if you have a organic compound, okay, organic compound, you know that inside that maybe it's organic compound, or you does not, your sample is unknown sample, you have no idea what inside that, maybe a tumor spectroscopy evaluation inside the tumor, you does not have any idea, you just want to analyze, okay, using NMR. Okay, so it helps to determine maybe the present, especially NMR actually usually, especially for the liquid NMR, we use the liquid NMR to determine the presence of compound. Okay, for example, if you want to determine the presence of maybe a fatty acid, okay, in certain samples, okay, you want to determine the presence of maybe a targeted compound in certain samples, okay, in unknown sample, but you need to know what is your target compound, okay, from the unknown sample. Then, based on the targeted compound structure, you can predict where does this signal will appear, will be observed, okay. Mostly for this castle, we just suggest to run the proton NMR first, okay, because you just want to predict, is it maybe that targeted compound present in your unknown compound, in your unknown sample. Okay, I think most of the sample that sent to our lab, usually they want to detect the presence of certain compounds in their unknown sample, like a liquid sample or the solid sample. They just give us, okay, the idea, this is, we want to detect this compound, okay. But if you want to, maybe you have unknown compound, you want to determine the structure, NMR also can help to determine. You have, for example, you already isolate, you already get that pure compound, pure isolated compound. Okay, you can run NMR, okay, experiment to determine the structure. Then you need to go to you need to run for proton, carbon, and also to the NMR analysis. Okay, if you just want to find you just want to targeted compound presence or not in your unknown sample, just go for proton experiment. Okay. Mr. Fikri,
Okay.
are your questions? Then the next question kan from
The
Malaha
next
from
one, yes,
Zulhanafi.
yes, yes. From Zohanafi, he asked, can we use the NMR to measure the absorption level of fatty acid on metal surface?
Actually, for the absorption level, I don't think so. For the absorption level of fatty acid, if you just want to, you want to detect the absorption level, we cannot detect by using NMR. But if you want to detect either that fatty acid already absorbed on the metal surface, yes, you can. Mean that you run the metal surface to see, is it the fatty acid already been absorbed by the metal surface? Then you can run for NMR to reconfirm that your absorption reaction already happened. Then you can run for NMR. Okay. for the absorption level, no, you cannot detect because NMR is just to detect the liquid NMR, just to detect the presence of compounds. Okay. The next
Okay.
question will be from Coco.
From
Right.
copper again. Without that, can we still estimate C position of the structure?
Yes, you can still estimate if it's a known compound. It's a known compound. You can estimate based on the chemical shift range. Okay, if unknown sample, then you need to go for that. Okay, if a known compound, you can still predict or estimate the position of carbon based on the chemical shift range. For example, you know that the chemical shift range for methyl, for example, methyl, CH3, CH2, hydrocarbons is in the downfield region around 0 to 70 ppm. Okay, and then for aromatic carbon is around maybe up to maybe 80 up to 100, 110, 120. And then for carbonyl, you know that the carbonyl acids around 165. And then for the carbonyl ketone, okay, so based on the chemical shifting given, you can predict, you can estimate the carbon position. But if you have no idea, okay, you have no idea the structure of the compound, your compound is unknown, the structure is unknown, then you need to write for depth, and then together couple with the helps of 2D NMR analysis also, the COSY, HMBC, HSQC, and also HMQC. Okay, welcome, Mr. Fikri.
Okay, is there any questions from the audience? Please raise, unmute, you mute your mic. Okay, that's fine. Yeah.
Accent from exam Megat. Can NMR detect isomerism? What type of isomerism? It is kalau if it geometrical isomer, cis and trans, yes, you can use. Okay. But if a chiral, if you meaning of a chiral compound, I don't think so. Using NMR liquid can detect. As much I know, we cannot use NMR to detect the isomerism. Like maybe you want to detect the isomerism, the chiral carbon. I don't think so. We can detect using NMR. Okay. Welcome.
Okay. There's any more questions from the audience?
It's
You
okay.
can ask directly or
I already
just give in the chat.
email, right? So if you have something regarding NMR, you want in future, if you have something to ask regarding the NMR, especially the liquid NMR, you want to maybe helps you to reconfirm the structure, to analyze, helps you to analyze, or you want to do something with NMR, you want to know either is it possible to run the NMR for certain experiment, for certain analysis, you can just personally email me. Then I will give I will help. Okay.
Okay. Okay. Thank you, Doctor. So that's the end of our webinar today. We hope that you have gained some new knowledge so that you can implement them in your study and research. Don't forget to visit the UTM University Laboratory Management Center Facebook and our official website for more information about our instrument services. See you again on the last slot of Bicara Pakar URL 2022 webinar for series entitled Ask an Expert Particle Size Analyzer by Dr. Ernieyanti Muhammad Noor tomorrow, 28 February 2022 at 10 a.m. Thank you, Doctor. And for the audience, stay safe. Assalamualaikum warahmatullahi wabarakatuh.